Hello again. Um, let's now in this video clip I want to talk about magnitude of the vector. Okay, sometime you can call it modulus as well. Okay, it's look like an absolute value, but you will put two vertical lines on the left side and the right side. That's the contrast from the absolute value, but yeah, the concept is pretty much the same. Remember when we studied the absolute value, another definition of absolute value of a number is the distance between that number and the point 0. Okay, so in this case, we are going to study the vector in 2-dimensional and 3-dimensional space, right? The magnitude, or the sometimes we call it length or norm, or as I said, you can also call it modulus of the vector is the distance between the initial, which is the origin, okay, origin, and the terminal point of that vector, okay, and we denote it by this notation, okay, what to call it, but yeah, it's this notation, and we call it magnitude, okay, or length or norm of vector A, okay. All right, it's in 2-dimensional. The way we find the norm of vector A or magnitude of vector A is by using the Pythagorean theorem. So suppose vector A can be written as the order pair A1 and A2. Then the length of vector A, or the modulus of vector A, can be computed by using this formula. You do find the absolute value of A1 square plus A2 square, okay? And I will explain why we get that. And it's the same way you do when you have the point here. This is the point A1 and A2, right? And you want to find the distance from the origin 0 and 0, okay? And that's the same formula that you have to use to study the distance between 2 points. And this come up with the point 0, 0 and A1 and A2. So that's why we need this formula. Okay, A1 square plus A2 square and everything under the square root. Okay. The generalization to the 3-dimensional vector space. So given that you have the point here, the point, the terminal point of vector A, okay, and then you also have the origin 0, 0, 0, okay, and you want to find the length of the vector. In the 2-dimensional vector space, you use the Pythagorean theorem, and this time you're going to use the generalization of Pythagorean theorem. Sometimes people call it Euclidean norm, okay. The way you find it, you just square each component and add them up, and then you take the square root of everything you get, okay. That's the way you find the length of the vector in 3-dimensional space, okay. Now in general, okay, if you want to find the norm of vector P and Q, okay, remember the way you find the vector P and Q is you do subtraction, P minus Q from last EP that I talked about, right? You do Q minus P, and then you get this result here. And if you want to find the norm of vector P Q, you just do the same way from the definition. You take each component square and then add them up, and then put everything under the square root, okay. All right, perfect. Another property that you need to understand or remember, if you have the scalar k times vector v, and you want to find the modulus of the new vector kv, is to take out the k, but sometimes k is negative, right? So you need to take the square root. By the way, let me mention this. the resulting of the magnitude or the length of the vector is always either 0 or positive. Okay, the 0 is have in only one case, even only if that vector is a 0 vector. Okay, but if it's not a 0 vector, the length is always positive. Okay, so when you take out the k, you need to take out the absolute k actually, right? Because if k is negative, you take it out, you get a positive back. Okay. Right. Next, let's talk about the fundamental vector. Actually, we can call it basic vector, I, j, k. Okay, I, j, and k here. They are important in the case of, if you wanna understand. Well, let me explain you this way. In any vector, assuming we are considering in the two-dimensional space, any vector can be written as the linear combination of vector I and j. Okay, so we call I and j the basic vector. If you want to understand more detail about this, you have to study linear algebra. Okay, the same concept for the three-dimensional space. You have I, j, and k. Any vector in three-dimensional space can be written as the linear combination of vector I, j, and k. Right. And now let's take a look at what I and j and k are, and how can we write them as an order pair. Okay, vector I is a unit vector line on the x-axis. So in two-dimensional, we can write vector I as the order pair 1, 0. I think that there's a typo here. Let me fix it. This should be 1, 0. Okay, it's 1, 0. So vector I is the order pair 1, 0. And vector j here is the order pair 0, 1. Okay. All right. And for the case of three-dimensional space, all right, we have ij and also k, right? I is 1, 0, 0. It's just generalization from the two-dimensional. In two-dimensional, you only have 1, 0, and then you extend it to one more coordinate, right? So you get 1, 0, 0. For j is 0, 1, 0. And for k, the new one is going to be 0, 0, 1. That's for k, and it stands for the unit vector on the z axis. Okay. From the definition of I, j, and k, you can find the modulus of them, or the length of them. It's just 1, right? You can see from the picture here, it's so obvious that the length of vector I, vector j, and vector k are 1. Okay. And sometimes, as I said, sometimes we call them standard unit vector. And or just put the standard in front. That should be more common. Okay. Unit vector I and unit vector j are the basis for the system. I just explained this to you. Okay. We call them the basis, and the reason that we call them the basis is because any vector in the two-dimensional space can be written as the linear combination of vector I and vector j. Okay. For the three-dimensional, same holds. So you have I, j, and k on the basis. Okay. And here's an example that every vector in two-dimensional and three-dimensional space can be written as the linear combination of the standard unit vector. For example, given the point, the vector of v, v1, v2, and v3, you can write this vector as a linear combination of I, j, and k by multiplying the scalar v1 to the vector I, scalar v2 to the vector k, and scalar v3 to the vector j. Sorry, I make a mistake. Let me revise it a little bit. v1 multiplied by vector I, v2 multiplied by vector j, and v3 multiplied by vector k. Okay, that is the way you explain why any vector can be written as the linear combination of the standard unit vector. For example, here you have vector 2, -3, and 4. Then you can write this vector as 2i minus 3j plus 4k. That's the linear combination of vector I, j, and k, right, as I said. And another example, vector 0, 3, 0, you have 3j, right? And then you can treat, well, if you want to complete it, you want to see why I and k disappear. Well, it doesn't disappear, but you can write it as 0 times I plus 3j and plus 0k. Okay, but 0 times vector is just 0 vector, right? Okay, that's the reason why you don't have to write them, and you just leave 3j only. Okay, that's modulus, definition of modulus and some property. And then yeah, and then I wanna continue to this unit vector. Well, you already know some example of unit vector, which are the standard unit vector I, j, and k. Alright, and then sometime you might have to do this. Given the point, the vector A, and then you want to find a new vector which is called unit vector that has the same direction of A. Okay, a unit vector is a vector having unit magnitude, or in other words, magnitude is 1. Okay, given a vector A with a magnitude norm of A, right, then A divided by scale, actually, to be precise, I have to write this down. You have the scalar 1 over the modulus of A. This is the scalar, right? And then you multiply it by vector A. Is the unit vector having the same direction as vector A? Okay. So it's pretty much like a vector A. If A is already a unit vector, then you don't have to do anything, you know. But if A is have magnitude beyond 1 or less than 1, you then you do the standardization to make it unit vector or having the magnitude 1. Okay, normalize it. In other words, you normalize it. Okay. Okay. Right, let's take a look at this example. You have a unit, you want to find a unit vector in the same direction of vector 3w minus v. Okay, if the vector w is 2, -1, and 2. Okay, if, well, you have this notation, you can also change your notation. In some students understand this notation better. You know, you have 2, -1, and 2. How do we get them? You just take a look at a number in front of I, in front of j, and in front of k. So you get 2, -1, and 2. For vector vector v is just 3, 4, and -5. Okay. And you want to find a unit vector in the same direction of this guy, right? From the definition above, you need to find the modulus of 3w minus v. And then, well, you just first compute the vector 3w minus v. You get 3i minus 7j plus 11k. And then you find the modulus of this vector. You get, there's a mistake here. You have 3 square plus -7 square plus 11 square. Let me check this if it's right. So you would have 9 plus 49 plus 121, and that should be okay. It's square root of 179. Okay, that's the modulus of this vector. And then you want to find a unit vector have the same direction of the original vector 3w and minus v. So then you just write down the original vector here. This is the original vector, and then multiplied by the modulus square root of 179 here. Okay, that's the new vector. Okay, all right, let me finish this up by talking about the basic property of the vector. If you are given 3 original vector with the scalar, this is the algebra of the vector, and then I will finish this EP up, and then I will leave the rest to the next video clip. All right, so the basic property, you have the a commutative property, commutative of the addition. You have the associative. Okay, this is the associative, and you have unit vector. Sorry, not unit. Zero vector is the identity, right, for the addition, and you have inverse for the identity for the addition, which is a negative of vector u here. You have scalar multiplication, number 5, and you have a unitary property, which is you have the scalar 1 multiplied by the vector u, you get the same vector u here. All right, that's a basic property. I think it's so common, you have to understand. It's really natural, right? So yeah, so sometimes you use them without thinking about the rules, so just use the property here. Okay, for the next video clip I will talk about dot product. For this one, thank you very much for watching, and see you next time. Bye bye.